So when you take these Fibonacci numbers and you divide them, and the bigger they get, when you take the bigger divided by the smaller, like for instance here, 89 divided by the 55, you get this number. Now that is a special thing called phi. And it's a Greek letter, and phi is kind of like pi. It's a number that goes on forever and never repeats. And there's so many interesting uses for this. It's called the golden ratio. Now, the people that were building ancient art and ancient buildings knew this ratio. Even though they didn't have calculators, they knew this number because they thought it was the most beautiful ratio that existed. And it's found on the human body as many as 50 times. I'll give you an example. If you lay your arm out on your table, just this part of your arm. Very easy to see, okay? Now, this part, which you would consider your forearm, goes from your elbow up to your wrist, okay? If you take that part, and then you divide that by the smaller part, which is from your wrist to the end of your fingertips, take the bigger, divide it by the smaller, you get 1.618. That's the ratio. And of course, it's the same on the other arm, duh, right? Now hold your hand in front of you. Now, put your fingers together, kind of like a pedal, right? If you take the width of your hand, including your thumb, and the length of your hand, and you divide them, you get 1.618 again. That same ratio. The bigger divided by the smaller, 1.618. Now, look at a particular finger. I'm very tempted to hold up my middle finger right now, but I'm not. I'm going to choose the pointer finger. All right, but any of the fingers will work. You know how you have a knuckle, two knuckles, and that divides your finger into three parts? There's three bones there, right? Okay, take the middle one and compare the middle section to the smaller section, and if you take the bigger one, divided by the smaller one, 1.618 again. That line is not exactly in the middle of your two, the crack where your knuckle is not exactly in the middle. It's at that special ratio, the bigger divided by the smaller. And then if you go to, there's three sections of knuckle, you compare the middle section to the bone that would go from the palm to the first knuckle, the bigger divided by the smaller, 1.618 again. The width of your face, the height of your face. Now this is up to where your hairline is. Bigger divided by the smaller, 1.618. It is on you all over the place. I'll give you another example. If I take this stick, where is the right one for me? I think it might be this one. Okay, you take this stick and you take the bigger part. See how I marked the 1.618 mark? That's the golden ratio. It's the bigger divided by the smaller, 1.618, that mark right there. And here, look at how this matches up. Guess what's right there? My belly button. That's exactly where the belly button is supposed to be, at the ratio of the bigger part divided by the smaller part, 1.618. If I hold out the stick like this, and if my fingers go past it, which they do, that means my arms are extra long. Did you know that your wingspan and your height are supposed to be exactly the same? Well, mine, I stick out. So that means I have extra long arms. Or maybe my shoulders are extra flexible to be able to reach out further than I'm supposed to. All right. And then do you see that mark right there on the stick? Again, 1.618 again. That distance compared to the whole rest of me, the bigger divided by the smaller, 1.618. And if I flip it around, big shock, same thing happens over here. That mark, right exactly at the right spot to make the bigger divided by the smaller, 1.618. It's all over the place on the human being. And I think that's fascinating that we have that ratio over and over and over and over on us. All right. So later this hour, I will have you grab the right stick for you, because I got one for every height. Unless you're taller than 6'3", or shorter than 4'11", I got a stick for you. All right. So let's move on. Factoring. That's what we're talking about today. So, factoring. Didn't we already do factoring? Yes, but now we get to do hardcore factoring. This is the part where I believe that we will be factoring things that are harder than any other math class you will ever have. This is like the highest level factoring that I think you will ever do. I could see maybe like a stumper problem in BC calculus, maybe has something harder than this, but they usually don't go this hardcore in factoring. All right, so we're going to learn some really heavy-duty factoring. Now, to do this, you've got to know some rules. All the same rules I've told you before, they're the same rules. I just got to remind you of them. The first thing we always do in factoring is look for a GCF. So look at number 1 here. If you haven't already found it, I asked you to find your worksheet, and I'm just going to do your worksheet with you. Do you see something in common in all 3 parts of this, all 3 terms? Is there anything that's in all 3 terms? No. Then you can't factor out a GCF. All right, now I want to take 2 seconds to remind you, the lead term on this thing is the x to the 4th. What is the number 4? There's a name for it.
Degree.
It's a degree. Very good. This is a 4th degree polynomial. All right. Now another thing about that 4, that degree, that means there's 4 solutions to this equation. There's 4 answers. Now we don't know what the 4 answers are, but we know that there are 4. Okay, if you look at the next problem, problem number 2, see how the biggest degree is 3, so this is a degree 3. That means there's going to be 3 answers on this one. All right, so we're going to factor this out. There's going to be 4 answers. The fact that it leads with a positive number, there is no negative in the front, means the right end is doing what? It's going up. Good. The fact that this is even means the other end will either be the same or different, and what is it? If it's even, is it going to be the same or different? Same. Even degree means they'll be the same on both ends. All right, so there's a little bit of review. But now, back to factoring. There was no GCF to pull out, so then you used to go to 2 sets of parentheses. Now, all the rules I told you still apply. The first 2 spots are for the x. But do you think if I just put an x and an x, it's going to make x to the 4th? That doesn't make any sense. Somebody's gut feeling is going to be right on this. What do you think I should put there instead? X squared and x squared. Very good. Next, we always do the signs. You with me? Next is the signs. And it's either plus minus or plus plus or minus minus. So here's some rules on that in case you forgot them. Is there a negative in the problem? Then there will be a negative here. Period. If there's a negative in the problem, the first spot, you might as well make it negative. Then the question is, whether it's a negative and a positive or a negative and a negative. That's your only 2 choices now. Look at the last number. If the last number is negative, then it has to be a positive and a negative. And since it's not, it can't be a positive and a negative. So what is it? Negative, negative. Has to be. See how we're using logic here? If it isn't this, then it has to be that. If it isn't plus minus, then it has to be minus minus. There has to be a negative in the problem in the first place because there's a negative in the original part. All right. And then the last thing, it's either 6 times 6 makes 36 or 9 times 4. And do you know that if I use 6 and 6, just in your head quick, if you just go 6 and 6, do you think that's going to make a 13? Of course not. So then it's not 6 and 6. What is it? 9 and 4. There, it's factored, but it's not factored all the way. This is a very common mistake. You feel good that you got it factored and you think you're done. Well, I want to remind you, for instance, if you had to reduce 50 over 100 and some kid tells you, well, I reduced it to 5 over 10. You'd probably say, okay, well, that's a good start, but you didn't actually finish it. Same idea. I got to finish it. I got to go all the way. I got to factor this again and again. It's going to have 4 parts. How could I have known it was going to have 4 parts? Because it's to the 4th. Do you remember how to factor that kind? It's called the difference of squares. Zola, Tell me what x squared minus 9 factors to. X plus something and x plus something. What do you think it is? 9 and 1? Nope, because, let me just show you, if I put a 9 and a 1, I'll end up with 9x and 1x. That makes 10x in the middle. There's no 10x in the middle, so that can't work. So it's not 9 and 1. What other choices do you have?
3 and 3.
Must be 3 and 3. And remember, it's got to be a plus and a minus. How do I know? Because there's a negative in the problem, so there must be one negative. The last number's negative tells me it's a plus and a minus. 3 and 3. Just like that one. Steichen, I bet you can do this last part.
Plus 2 and a negative 2.
Yep. There you go. Now, I am not going to make you write x plus 3 equals 0 and solve it for all of these. That'd be dumb. But you got to know what you're doing. What you're doing is figuring out what can I put in here that makes it equal 0. X equals negative 3. What can I put in here that makes it equal 0? X equals 3. And I'm not going to make you write x equals x equals x equals every single time. What you can do is write x equals, and then what are my 4 answers? Negative 3, 3, negative 2, and 2. In factored form, that's just this. I wouldn't make you recopy that. If I drew a line like that, that'd be good enough. Okay, now what is this x-intercept thing? All right, let's talk about that. The zeros, are they just always the x-intercepts? No, they aren't. Let me explain why. Let's say I had these 4 answers. X equals I, x equals negative I. If you ever have an imaginary, you're going to have a plus it and a minus it. You'll always have 2 imaginaries. If you have an imaginary at all, they come in sets of 2. Then, let's say I had another answer that's x equals 8, and another answer that's x equals 7. Well, do you know that that means there's 4 answers, but only 2 of them are x-intercepts? Do you get these can't be x-intercepts? They're not real. You can't see them on the graph. But they're answers. They're just not x-intercepts. This kind, the real kind, those are x-intercepts. So back to our question, what are the x-intercepts? All 4 of them are. They're all real. How would they ever not be real? If you get an I when you're solving it, then they'll be imaginary. So these are all real. So there's 4 x-intercepts. Let me show you one again. Let's say, please go off to the side and write this. X squared plus 4 and x minus 1. If you had factored it to this, you will get answers like this today. This part's super easy. It's x equals 1. That's real, and it's an x-intercept. But this, please write this. X squared plus 4 equals 0. And solve it. That is literally right off our last test. The test about complex numbers, where you get a real part and an imaginary part. This is going to be imaginaries. Did you remember the absolute value? I'm up to like 3/4 of you are remembering that now. You can keep losing points if you want to. If you remember this, see, then you'll go, oh, x isn't alone yet. Oh, yeah, there's 2 answers. 2i and negative 2i. Do you remember me telling you if there's ever an imaginary, there'll be 2? Look at that, there's 2. Okay, so 2i, negative 2i. Are those real? No. Are those x-intercepts? They are not x-intercepts. Only real things can be x-intercepts. That's real, and that's an x-intercept. That's not. Now, if I wanted to write it as an x-intercept, x-intercepts have y equals 0. I might write it as 1, 0. But these guys, they're not real, so they can't be x-intercepts. All right, I hope that answers your questions about number of x-intercepts is really kind of saying how many real answers do you have. All right, let's go on to this one. Now for this one, I have to teach you a different kind of factoring. You look for the GCF, there isn't one, so you can't do it that way. You look for 2 sets of parentheses and you'll realize I can't do it. There's no way to do this. So we have to do a new kind of factoring called divide and conquer. Let me explain a little bit of the background. Did you know that during World War II, we were trying to land troops in Europe to help out against the Germans? Okay? And we had 2 beaches we could pick from. They knew that we had 2 beaches we could pick from. And we needed to keep it secret which beach we were going to go to. Okay? So that they would have to divide their army into 2 parts. Because if you're going to set up your defenses, you're not just going to pick one of the 2. You got to guard both. Because if you just pick one of the 2, well, then we would just switch. You know, like we'd see, holy crap, all their guys are up north. We're going to go south. You know what I mean? So you make them divide their army into 2 parts. But even more, we decided to have an incredibly complicated fake. We faked to the north, and it was so complicated, there was like 16 parts to the plan. I don't want to go into it because it take too much out of the class, but we faked Hitler out bad. He thought for sure we were going north. He was positive. So he not only split his forces up, he put his best forces up north. We went to the south. What's the name of the beach we landed on? In Normandy. Good. So we ended up still getting slaughtered as we came up the beach. We lost so many guys all at once. But thankfully, enough of them survived that they could form a beachhead and then they could spread in from there. Because otherwise, if they would have had their best divisions there, their best guys, their best ammunition, their best weapons, they would probably killed everybody. And then it would have been GG. We would have lost. We'd all be speaking German right now. It was that important. So, divide and conquer has been a battle strategy since back to Genghis Khan. But we do it in math too. Let me show you. Draw a line and divide this up into 2 sets of 2. Because then you can factor them separately half at a time. You're going up against only half the problem, and then you can factor it. Do you see a GCF in here? I do. What do they both have in it? X squared. Then put a parenthesis, and hopefully you've learned how to factor out something. This is so important. If you haven't figured this out yet, you've got to come in the morning and get some extra help. Because if you don't know how to factor the easy stuff, holy crap, you're going to die in this next test. So come in and get some help if your factoring is weak, even the easy stuff. All right, so I'm factoring out that x squared. A reminder what that really means. We divide this by x squared and we divide that by x squared, and we would have x plus 1. All right, now on this next part, you have a choice. You could either factor out -4 or regular 4. I would pick -4, and the reason I know that is because I know that I want this to match this. I want them to come out the same. And if I factored out a regular 4, I'd have minuses in both spots, and that's not going to be the same. By factoring out the -4, divide by -4, divide by -4. I hate having to show this, but for the people that are just learning how it works, x plus 1. Do you think it's a coincidence that these came out exactly the same? No, that's on purpose. Now this next stage is going to separate the people that get this from the people that don't. So pay attention on this next part. Anybody could have just factored those 2 things separately, but can you put it all together? Do you remember me saying always look for a GCF? This term and this term now have a GCF. What is the common factor between both of those things I circled in red? What's the thing in common? X plus 1. So that's the GCF, and you factor it out to the front. Do you get they both have an X plus 1? So that's what factors out to the front. Now, what do you do when you're factoring? You're really dividing by X plus 1. Do you have to show this? No, I'm just showing it for people that don't really get it. Then this would cancel this, and this would cancel that. And what do I have left? X squared and a minus 4. And I hope you realize that that can be factored again. The X plus 1 is still X plus 1, but this part can be factored to two things. Tomas, what are those two things? Plus 2 and minus 2. Now I got 3 answers. Do they feel real to you? Yes, then they're x-intercepts. They're real and they're x-intercepts. And look, we expected 3 answers because the degree was 3. If it's got degree 3, you're going to get 3 answers. Are they always real? No. Sometimes they're real, sometimes they're not. These are all real. How do you tell if they're imaginary? They'll look like this, except they'll say plus in the middle. They'll look like this, but they'll say plus. They'll show you one like that in a minute. All right, let's go to this one. I'm not filling in every blank. You have to do some work here. I'm helping you with learning how to do these, but you got to go out to the right-hand side and fill in the answers in the blanks. All right, on this one, we finally have a GCF. Factor it out. Put it here. Did you realize that 2x was the thing that comes out of each of them? And again, if you need the training wheels, I don't, but I'm doing it just to show you. That's what you do. And then you go, that gives me x squared, plus that gives me 2x, minus that gives me 15. And I hope you can finish factoring it. And then I hope you know that there's 3 answers because the problem was degree 3. Of course there's 3 answers. What are those rules again? Oh yeah, there's a minus in the problem. There has to be a minus in the answer. The last number is negative. Ooh, it's got to be a minus and a plus. Multiplies to 15 is probably a 5 and a 3. I'm just going to be careful where I put the 5. If I by accident had put those backwards, I would have got negative 2x. And then I would have just switched the signs. Because whenever you get the opposite of what you want, you switch the signs. All right, now here's where a few kids fall off. Because they're like, I get this answer, but what's that answer? Really, the question is, what makes it equal 0? What makes this equal 0? If x was negative 5. What makes this equal 0? If x was 3. What makes this equal 0? If x was 0. So you're finding a thing you can put in for x. If you put in negative 5, it makes that part 0. If you put in 3, it makes that part 0. And if you put in 0, it makes that part 0. Do those answers look real to you? How can you tell? Well, did you ever do a square root of a negative? Well, then they're real. All right. And then that means they're x-intercepts. Number 4 here. There's number 4. It's another divide and conquer. Now, you have 2 choices on this. you can notice that there's a GCF and factor it out. Or, and that's good, if you do that, all the numbers will get cut in half. They're easier to work with. But if you didn't notice, it would still work. You could still divide and conquer it. But do you agree they all have a 2 in them? So then it's probably smartest to just get them all cut in half and put a 2 in front. Now my numbers are all half as big. Okay, I know you just learned divide and conquer. So this is an important moment where I got to just remind you to keep bringing the 2 down. Don't forget that 2 just comes down. And divide it right down the middle. Factor that part, and you might be like, there's nothing I can factor out of this. And that's kind of true. So you factor a 1 out of it. Trust me. If you can't factor anything else out of it, and you have to factor it, then factor out a 1. Let's see if you can finish this one. I'm going to pause for a minute. Okay, here's a little checkpoint along the way. Did you get this far? Did you notice that the only thing you could take out of both of these was an x squared? And what was left would be a 4x plus 9. And then I said that I should weirdly factor out a 1 here. That's so that you'll still have a 4x plus 9 here. Coincidence that these are identical? No, it's a sign you're doing it right. Of course they have to be the same. Now there's 2 kinds of kids. The kind of kid who's still bringing this 2 down and the kid who's going to forget it. If you forget to bring that 2 down, you will lose credit for the whole problem because that 2 is part of the answer and it needs to keep coming down. Now, the GCF in here, the thing that's in common, is the 4x plus 9. And I don't want to do the training wheels anymore where I divide everything by 4x plus 9. I can just kind of look and see what would happen if I canceled out the 4x plus 9s, and I'd have an x squared plus 1 left. Raise your hand if you had that one right. Okay. Some of you have already got this. That's called factor by grouping. All right. So now we're supposed to get our answers, and this is the first time we're going to get some imaginary ones. That 2 confuses a lot of people, and I keep reminding you what we're doing. What x could you put into it that would make it 0? You can't. There isn't any x over there. There's no number there. There's no way to put a number in other than 2. It's not a variable. So there's no answer for that 2. If they had an x there, there'd be an answer. There's no answer for that 2. It's what x can you put in. So this one, what x could you put in? Hint, it's a fraction. -9/4. Now, if you can't do that in your head, you got to go 4x plus 9 equals 0 and solve it. 4x equals -9. Divide by 4, divide by 4, -9/4. Cool. And the last one, x squared plus 1 equals 0. Subtract 1 from both sides. X squared equals -1. Square root of -1. Haha, told you there was going to be imaginaries. And I'm probably up to 2/3 of you guys now know that this is absolute value of x. Otherwise, you think the answer is just I, but it's actually got 2 answers. X isn't alone yet. Now it is. X equals I, and x equals I. That'd be dumb. That's not the exact same thing. So then you go, oh yeah, that's right, -I. And I have 3 answers. A 1, and a 2, and a 3. And that's what I expected to have because the problem was degree 3. And I got 3 answers. only one of them's real, and therefore only one of them's an x-intercept. These are answers, they're just not real, and they're not x-intercepts then. All right. All right. Oops. Now the back side of the worksheet, I'm only going to give you a little reminder, and then the rest is yours to complete in class. Your job, finish this sucker up in class. There's one factoring problem right there. It'll be good for you to practice that divide and conquer kind of factoring. And on this, I want to remind you, the lead term is something like this. And it'd be really handy to have that, because then you'd know your leading coefficient, you'd know your end behavior, because, you know, if it's negative in front, it's going down on the right. I totally made this up. Just find your own right answer. You put together all the things in the front, and don't forget the powers too. It'll tell you, if you get this thing, it'll tell you the degree, it'll tell you the leading coefficient, it'll tell you the end behavior. X-intercepts, you get that by figuring out what makes this 0. Wait, change to red. What makes this 0? What makes this 0? What makes this 0? What makes this 0? That's how you get your x-intercepts. And if any of them are imaginary, they won't be x-intercepts. All right. So, your job, finish up this worksheet. Got kids right next to you that are doing the same problems. Don't be afraid to ask. Also, can come up and ask me. And that's all I got for the video for today.